Introduction. Father, this park is so beautiful. It has so many swings and rounds to enjoy. My friends also come here daily. I know that you must like this park. That's why I brought you today here. Thank you, Father. Most welcome, son. Suddenly, earthquake occurs. Are you all right, son? Yes, Father. I'm okay. May I ask you something? Yes, sure. How earthquake occurs? And how can it produce so much destruction? When sliding of the plates occur in the interior of the earth, it causes earthquakes. The shock wave from this sudden movements come to the surface. These waves move along the earth's surface and cause most of the damage. Okay, Father. Now I got the point. And I want to know more about these waves. Okay, son. I will tell you. Children, today we will study more about the waves. Objectives. At the end of this lesson, you will be able to define wave motion, differentiate transverse and longitudinal waves, evaluate displacement relation in a progressive motion, calculate speed of a traveling wave, understand superposition of waves, know about reflection of waves, define stationary waves, understand beats, analyze Doppler effect. Definition. By means of waves, transferring of energy is possible without bulk motion of matter. Wave motion may be defined as a form of disturbance which is due to the repeated periodic vibrations of the particles of the medium about their mean positions, and the motion is handed over from one particle to the other without any net transport of the medium. A stone is dropped in the water. A boy talking with someone. Earthquake are some examples of wave motion. In this chapter, we shall study about mechanical wave motion. Mechanical waves can be produced and propagated only in those material media which possesses elasticity and inertia. These waves are also called elastic waves. Transverse and longitudinal waves. A transverse wave is the wave in which all the medium particles perform simple harmonic motion about their own mean equilibrium position in a direction perpendicular to the direction of wave propagation. Longitudinal wave motion is that wave motion in which the individual particles of the medium execute simple harmonic motion about their mean positions along the direction of propagation of the wave. Transverse and longitudinal waves. Let's make difference between transverse waves and longitudinal waves. Number 1. In transverse waves, the particle of the medium vibrate at the right angles to the direction of propagation of the wave, whereas in longitudinal waves, the particles of the medium vibrate along the direction of propagation of the wave. Number 2. The transverse waves travel in the form of alternate crests and troughs. One crest and one trough constitute one wave, whereas the longitudinal wave travel in the form of alternate compressions. One compression and one rarefaction constitute one wave. Number 3. Transverse wave can be formed in solids and on the surface of liquids only, whereas longitudinal waves can be formed in any medium. Number 4. When transverse waves propagate, there are no pressure changes in the medium, but when longitudinal waves propagate, there are pressure changes in the medium. Number 5. Transverse waves can be directly represented by a sine curve, whereas longitudinal waves can be only indirectly represented by a sine curve. Number 6. Transverse waves can be polarized, whereas longitudinal waves cannot be polarized. Displacement relation in a progressive motion. A displacement time function at every instant gives the shape of the wave at that instant. It also describes the motion of the constituent of the medium at that location. A sinusoidal traveling wave is then described by y is equal to a sine kx minus omega t, where y is equal to displacement as a function of position x and time t. A is equal to amplitude of a wave. Omega is equal to angular frequency of the wave. K is equal to angular wave number. Amplitude. A represents the maximum displacement of the constituents of the medium from their equilibrium position. It is called the amplitude of the wave. Wavelength. The minimum distance between 2 points having the same phase is called the wavelength of the wave, usually denoted by lambda. For simplicity, we can say that the wavelength is the distance between two consecutive crests or troughs in a wave. Period. The period of oscillation of the wave is the time it takes for an element to complete one full oscillation. Speed of a traveling wave. A general relation for all progressive waves is given by v is equal to lambda upon t. In the time required for one full oscillation by any constituent of the medium, the wave pattern travels a distance equal to the wavelength of the wave. Speed of a transverse wave on stretched string. Suppose a string is stretched between two rigid supports. If the string is slightly disturbed by plucking, it is observed that a hump travels with a definite velocity along the length of the string. The velocity with which the hump travels depends on the tension and mass per unit length of the string. The velocity with which a disturbance travels on a stretched string is given by C is equal to under root T upon mu, where T is equal to tension in the string, mu is equal to mass per unit length. Now, a string fixed at one end is stretched by hanging a weight from its other end. The tension in a string is related to the elastic property and inertia of the string. On stretching, the velocity is given by C is equal to under root T upon pi r square rho.
Here,
R is equal to radius of the string. Rho is equal to density of the material. Speed of a longitudinal wave. The velocity of propagation of a longitudinal wave depends on the elasticity and density of the medium. Wave velocity is equal to under root elastic modulus upon density. Principle of superposition of waves. Principle of superposition of waves states that the displacement due to a number of waves acting simultaneously at a point in a medium is the vector sum of the displacement vectors due to each one of them acting separately. Let us take an example. Consider two pulses approaching each other. When the pulses cross each other, they combine to produce a resultant pulse. After crossing each other, they again begin to travel independently as if nothing had happened. This gives rise to the following three important cases of superposition of waves. Number 1. Two waves of the same frequency move with the same velocity in the same direction. This gives rise to the phenomenon of interference of waves. Number 2. Two waves of identical frequencies and amplitudes travel along the same path with the same speeds in the opposite directions. This gives rise to stationary waves. Number 3. Two waves of slightly different frequencies moving with the same velocity in the same direction gives rise to the phenomenon of beats. Reflection of waves. When the wave strikes a rigid boundary, it completely gets reflected. And if the boundary is not rigid, then a part of the incident wave is reflected and a part is transmitted into the second medium. Let us take an example. A pulse traveling along a stretched string and being reflected by the boundary. The reflected wave has the same shape as the incident pulse, but it suffers a phase change of 180 degree on reflection. This is because the boundary is rigid and the disturbance must have zero displacement at all times at the boundary. When there is no boundary, then the reflected wave has the same shape and phase as the incident pulse. Stationary waves. The resultant wave formed by the superposition of two similar progressive waves traveling in the opposite direction is called a stationary wave. Antinodes. At some points, the displacement is always maximum compared to other points. These points vibrate with maximum amplitude and are called antinodes. The separation between successive antinodes is lambda by 2. Nodes. At some points, the displacement is always zero. These points, which are always stationary, are called nodes. The separation between successive nodes is lambda by 2. It is observed that the separation between a node and adjoining antinode is lambda by 4. Beats. When two sounding bodies of nearly the same frequency and same amplitude are sounded together, the resultant sound comprises of alternate maxima and minima. The phenomena of alternate waxing and waning of sound at regular intervals is called beats. Let's see an example. There are two harmonic waves, one of frequency 12 Hz and the other of frequency 10 Hz. When they superimpose on each other, they give rise to beats of frequency 2 Hz. The number of beats heard per second is called beat frequency. Beats are heard only when the difference in frequencies of two sounding bodies is not more than 10. This is due to persistence of hearing. The time from each loud sound to the next loud sound is called one beat period. Example. Let's take an example of beat. A tuning fork and an air column at 51 degrees Celsius produce 4 beats in 1 second when sounded together. The same tuning fork produces 1 beat per second when the temperature of the air column is reduced to 16 degrees Celsius. Determine the frequency of the tuning fork. Let's see the solution. When the temperature of the air column is decreased, the speed of the sound in the air column is decreased. Since V is equal to U divided by lambda, therefore V is decreased. Since the number of beats per second is less at lower temperature, therefore we conclude that the frequency of the air column is higher than the frequency of the tuning fork. Let V be the frequency of the tuning fork. Then at 51 degrees Celsius, the frequency of air column is N plus 4. At 16 degrees Celsius, the frequency of the air column is N plus 1. On calculating the given values, we get the frequency of the tuning fork is equal to 50 Hz. Doppler's effect. The apparent change in the frequency of sound when the source of sound, the observer and the medium are in relative motion is called Doppler's effect. Let us now discuss the apparent frequency of sound in different cases. Case 1. Source in motion, observer at rest, medium at rest. Suppose the source and the observer are separated by distance v, where v is the velocity of sound. Let nu be the frequency of sound emitted by the source. Now, the source starts moving towards the observer with velocity vs. It gives nu dash is equal to v upon lambda dash. On calculating, we get nu dash is equal to v upon v minus vs multiplied by nu. So, as the source of sound approaches the observer, the apparent frequency nu dash becomes greater than the true frequency nu. If the source is receding away from the observer, then the apparent frequency is given by nu dash is equal to v upon v plus vs multiplied by nu. Case 2. Observer in motion, source at rest, medium at rest. Observers move towards source with velocity v0. In 1 second, the observer receives waves occupying the space is equal to v plus v0. Number of waves in unit distance is equal to nu upon v. Number of waves in distance v plus v0 is equal to nu multiplied by v plus v0 upon v. Apparent frequency nu double dash is equal to V plus V naught upon V multiplied by nu. If the observer is moving away from the source, then the apparent frequency is given by nu double dash is equal to V minus V naught upon V multiplied by nu. Case 3. When both the source and the observer are moving towards each other. When both the source and the observer move towards each other, then apparent frequency is given by nu triple dash is equal to V plus V naught upon V minus Vs multiplied by nu. If both the source and observer move in the direction of sound, then nu triple dash is equal to V minus V naught upon V minus Vs multiplied by nu. Did you know? A mechanical wave is the disturbance produced in a material medium that transmits energy and momentum by traveling in the medium with a definite speed without any change in its own nature. As wind passes over the water's surface, friction force is to ripple. The strength of the wind, the distance the wind blows, that is fetch, and the length of the gust, that is duration, determines how big the ripples will become. During storms, the combination of low air pressure and onshore winds may produce a storm surge that raises the water level at the shore many meters above normal sea level. Summary. Let us summarize what we have learnt. Wave motion may be defined as a form of disturbance which is due to the repeated periodic vibrations of the particles of the medium about their mean positions. In transverse wave, all the medium particles perform simple harmonic motion about their own mean equilibrium position in a direction perpendicular to the direction of wave propagation. In longitudinal wave, the individual particles of the medium execute simple harmonic motion about their mean positions along the direction of propagation of the wave. The minimum distance between 2 points having the same phase is called the wavelength of the wave. The velocity of propagation of a longitudinal wave depends on the elasticity and density of the medium. The displacement due to a number of waves acting simultaneously at a point in a medium is the vector sum of the displacement vectors due to each one of them acting separately. The resultant wave formed by the superposition of two similar progressive waves traveling in opposite directions is called a stationary waves. The phenomenon of alternate waxing and waning of sound at regular intervals is called beats.